Dear students, today we are going to start first chapter in complex analysis, which is analytic functions. Now, what do we mean by analytic function? The function fz is said to be analytic at a point z is equal to a if there exists a neighborhood mod of z minus a less than delta at all points of which f dash z exists. Means if we take a point z is equal to a, and if we take a neighborhood of z is equal to a, and if in that neighborhood f dash z exists for all values of z, right, then we say that the function is analytic at the point z is equal to a. This is the analyticity at a point z is equal to a. If f dash z exists at every point of a domain D, now if we consider a domain D, and if derivative of fz exists at every point of a domain D except at a finite number of exceptional points, then fz is said to be analytic in the domain D. Now these exceptional points are called singular points or singularities of the function. So we shall study in more detail about singular points later on. Now we come to a very important result, which is known as Cauchy-Riemann equations. Now what are the necessary conditions for function fz to be analytic? If fz is equal to u plus iv is analytic in a domain D, then u and v must satisfy these equations. Del u upon del x is equal to del v upon del y, and del u upon del y is equal to minus del v upon del x, provided the four partial derivatives ux, uy, vx and vy exist. So these two equations, del u upon del x is equal to del v upon del y, and del u upon del y is equal to minus del v upon del x, these two equations are called Cauchy-Riemann equations. So if a function is analytic, that it must satisfy these two equations. Proof. Suppose that fz is equal to u plus iv be analytic in a domain D. Now because function is analytic, so its derivative will exist. So dw upon dz exists. So therefore dw upon dz has the same value along every path. Now if you take along x-axis, now what is delta z? Delta z is taken as delta x plus I times delta y. Now if we move along x-axis, then delta y is 0. So delta z will be equal to delta x. So therefore dw upon dz, which is by definition limit delta z tending to 0, delta w upon delta z. Now in place of delta z, we write here delta x. So this is limit delta x tending to 0, delta w upon delta x, which is del w upon del x. This is equation number 1. Now if we come along y-axis, then along y-axis what is delta x? Along y-axis delta x is 0. Change in x is 0. So delta z will be equal to I times delta y. So dw upon dz is equal to limit delta z tending to 0, delta w upon delta z. Now in place of delta z, we write here I times delta y. Multiply and divide by I, so in the denominator we shall have I square, right? And what is I square? I square is minus 1. So this is equal to minus I times del w upon del y. This is equation number 2. Now because the function is analytic, so therefore these two values must be same. So therefore equating 1 and 2, we have del w upon del x is equal to minus I times del w upon del y. Because w is u plus iv, so del w upon del x is del u upon del x plus I times del v upon del x is equal to minus I times del u upon del y is del u upon del y plus I times del v upon del y. So keep left hand side as it is, and the right hand side we multiply by minus I. Minus I into plus I is minus I square, which is plus 1. So therefore this side becomes del v upon del y minus I times del u upon del y. Now we equate real and imaginary parts. Real part on this side is del u upon del x. On this side it is del v upon del y. So del u upon del x is equal to del v upon del y. And if we equate imaginary part, we have del v upon del x is equal to minus del u upon del y. So these two equations are known as Cauchy-Riemann equations. Now remember one thing, that if a function is analytic, it must satisfy these two equations. But the converse is not true. Means if a function satisfies these two Cauchy-Riemann equations, then it does not imply that the function will always be analytic. So what are the sufficient conditions for a function to be analytic? The function w is equal to fz, which is equal to u plus y, is analytic in a domain D if it satisfies two conditions. The first condition is u and v are differentiable in D, and Cauchy-Riemann equation, that is ux is equal to vy, uy is equal to minus vx. These two equations are satisfied. And the second condition, the partial derivatives ux, vx, uy, vy are all continuous in D. So if a function f satisfies these two conditions, then the function will be analytic, right? Only satisfying Cauchy-Riemann equations will not imply that the function is analytic. So we shall see proof of this later on. Now we come to the polar form of Cauchy-Riemann equations. You know the relation between x Cartesian coordinates and polar coordinates. X is given by r cos theta and y is given by r sin theta. Okay, let's take this theorem. If fz is equal to u plus iv is an analytic function and z is equal to r into e to the power I theta, where u, v, r, theta are all real, then Cauchy-Riemann equations in polar form are given by del u upon del r is equal to 1 upon r del v upon del theta, and del v upon del r is equal to minus 1 upon r del u upon del theta. Now x is given by r cos theta, y is given by r sin theta. Now if we square and add these two terms, we shall have r square is equal to x square plus y square, and if we divide this by this, we will get tan theta is equal to y upon x. That means theta is equal to tan inverse of y upon x. Now we differentiate this r square is equal to x square plus y square partially with respect to x. So what will be derivative of r square partially with respect to x? It will be 2r into del r upon del x. Derivative of x square 2x. Derivative of y by y square, when we differentiate it partially with respect to x, will be 0. So 2r del r upon del x is 2x. That means del r upon del x is x upon r. Now what is x? X is r cos theta. So r will get cancelled and this is equal to cos theta. Similarly, if we differentiate this partially with respect to y, then we have 2r del r upon del y is equal to 2y. That means del r upon del y is equal to y upon r. And what is y? Y is r sin theta. So r will get cancelled and we have this is equal to sin theta. Now we differentiate theta partially with respect to x and y. So del theta upon del x is equal to, now I differentiate this tan inverse y upon x partially with respect to x. So firstly we will have 1 upon 1 plus y square upon x square multiplied by, differentiate this with respect to x taking y as constant. So we have minus y upon x square, which comes out to be minus y upon x square plus y square. Now in place of y we write down r sin theta, and in place of x square plus y square we write down r square. So which is equal to minus sin theta upon r. And now differentiate theta partially with respect to y. So we have del theta upon del y is equal to 1 upon 1 plus y square upon x square into derivative of y with respect to y is 1. So we are left with 1 upon x. Again you simplify it. and put x is equal to r cos theta, and we will get this as cos theta upon r. So del theta upon del x is minus sin theta upon r, del theta upon del y is cos theta upon r. Now we find out the four partial derivatives: del u upon del x, del v upon del y, del u upon del y, del v upon del x. Now what is del u upon del x? Del u upon del x is del u over del r into del r upon del x plus del u upon del theta into del theta upon del x. What is del r upon del x? We have found out here del r upon del x is cos theta. So in place of del r upon del x, we write cos theta. And what is del theta upon del x? Del theta upon del x is minus sin theta upon r. So del u upon del x comes out to be cos theta into del u upon del r minus sin theta upon r into del u upon del theta. Similarly, del v upon del y is del v upon del r into del r upon del y plus del v upon del theta into del theta upon del y. Substitute the values of the partial derivatives. So we have sin theta into del v upon del r plus cos theta upon r into del v upon del theta. Similarly, del u upon del y is del u upon del r upon del y plus del u over del theta upon del y. Substitute the values. Del r upon del y. What is del r upon del y? Del r upon del y is sin theta. So we put here sin theta into del u over del r. Similarly, del theta upon del y is cos theta upon r. So we have here cos theta upon r into del u upon del theta. And finally, del v upon del x is del v upon del r into del r upon del x plus del v upon del theta into del theta upon del x. Now del r upon del x is cos theta and del theta upon del x is minus sin theta upon r. So we get this. Now make use of Cauchy-Riemann equation. What is the first Cauchy-Riemann equation? First Cauchy-Riemann equation is del u upon we are taking second one first. Second equation is del u upon del y is equal to minus del v upon del x. Now what is del u upon del y? We have this expression sin theta del u upon del r plus cos theta upon r into del u upon del theta. And on the right hand side we have minus del v upon del x. So minus sign del v upon del x. So we have minus of cos theta del v upon del r plus sin theta upon r del v upon del theta. And the first Cauchy-Riemann equation is del u upon del x is del v upon del y. So put the values of del u upon del x from here and del v upon del y from here. Okay. So this was the first equation and this is the second equation. Now multiply 1 by sin theta and 2 by cos theta and add these two equations. Then we shall get del u upon del r is equal to 1 upon r del v upon del theta. Now put the value of del u upon del r is equal to 1 upon r del v upon del theta in equation number 1. So we have sin theta into value of del u upon del r is 1 upon r del v upon del theta plus cos theta upon r into del u upon del theta as it is minus cos theta del v upon del r plus sin theta upon r del v upon del theta. Now you can see from here these two terms will get cancelled. Cos theta will also get cancelled. So we are left with del v upon del r is equal to minus 1 upon r del u upon del theta. So these two equations are Cauchy-Riemann equations in the polar form. Now we can find out derivative of w in polar form also. dw upon dz is equal to e to the power minus I theta del u upon del r, which is equal to minus I upon r e to the power minus I theta del w upon del theta. Okay, this you can verify yourself or otherwise we'll do it later on. Thank you so much.